Swayam Prabha. Digital India. Educated India.
So far, we have discussed about the parameters such as catchment efficiency for the off-axial powder-based systems. However, if we talk about a realistic system for powder feed-based additive manufacturing, nowadays a coaxial nozzle is popularly used. So, a typical schematic of the coaxial nozzle is shown here, where you can see this black color thing is nothing but the nozzle. This is the central part of the nozzle, and this is the laser beam. As this is a cross section, you can see this is the cone through which the powder is coming. So, this is the powder stream. So, these are the powder particles going towards the molten pool created by the laser beam on the substrate. So, this is the substrate. So, unlike the last case, here you can see, so powder streams are like you are seeing in the cross section. Then later on, these powder streams, those are coming from, if it is a conical nozzle, everywhere in the cone. So, let me draw the cross section, for example, at a particular height. Let me assume to be here. The top view of the same for the powder stream will be something like this. There will be powder in this conical region, and center will be this laser. Then if you come down further, maybe at this particular location, if I will draw now the cross section, it will look something like this. So, this will be the powder everywhere, and center will be the laser. Further, if we go down, this diameter of the powder stream will further reduce, and it will attain its minimum value, and that is called as the focal point. Then after that, when the powder attain its minimum value, further it will start diverging, and its diameter will further increase. So, assume that is happening in the region number 3, and the diameter of the powder stream is further increased. So, let us classify this powder stream into 3 zones. First is zone 1. In the zone 1, the powder stream is having an annular cross section, as you are seeing here, like a donut. So, here the powder particles are in the periphery, but not at the center. Anywhere if you take the cross section, but it will remain same. This empty space will keep on reducing if you go down in zone 1. Further, when you reach to zone number 2, the empty region is completely gone, and the powder particles or the stream of the powder particle keeps on converging. So, this is the converging zone, zone 2. After attaining the minimum diameter of the powder stream, it will again start getting diverged, and that diversion will occur in zone number 3. So, the intersection of zone number 2 and zone number 3 is nothing but your focal point of the powder stream. Now, our focus is to find out what will be the mass input into the molten pool created by the laser beam at any focal point. Maybe you are defocusing your powder focal stream. That means you are not attaining this AB zone at the substrate. You are little bit lifting it up. In that case, your diameter of the powder stream will not be minimum. Also, it can be noticed that the laser diameter is going to be smaller than the powder stream. So we have to understand, it is very essential for us that how much powder is going to be inserted and or going to be participated in creating the bead onto the substrate. And if we come to know that how much will be this powder amount, then if we assume that the bead profile is parabolic, we can easily predict its height if width is known. And we know that width can be easily obtained by either applying the Rosenthal equation for a moving point heat source, or for more accuracy you can consider it to be as moving surface heat source. So basically the powder delivery nozzle follows a Gaussian distribution of powder particles in the 2D plane. So assume that this is your powder stream. I am right now considering a uniform cross section throughout along the z-axis, and the powder particles are moving towards the bottom part. Now if I take any slice, for example at a particular region and calling it as A, the distribution, if I just see the top view of the powder distribution at this particular slice, it will look something like this, and it usually follows a Gaussian distribution of powder particles. What does it says? The rule says the powder stream's spot radius at the focal plane is determined by the location at which the powder density is 1 by E square of the maximum. Fine. So there may be some particles outside, maybe 1 or 2, but this black color boundary is saying that outside this boundary the powder particles have been, the density of the powder particle is 1 by E square of the maximum value which is at the center. So following that, if I draw the particle number concentration at any point xy in the cross section in a slice, then it can be given by this curve. As you see, as I am moving away, means if the radius is increasing, the number of particles available or the concentration of the number of particle is keep on reducing. Mathematically, I can write it like this. It says the number of particle concentration at any point x comma y in a slice A will be equals to n naught exponential minus r square by k, where k is a constant and n naught is the peak particle number concentration at the stream center, right, at this location. And if r is the boundary radius at which the particle density is 1 by E square of the maximum, this particular boundary, we can easily obtain it. So let us write this boundary condition in this equation. It says at r equals to capital R, the number of particle concentration will be the 1 by E square of the maximum particle concentration, which is n naught. As a result, if I replace this equation here, I will get this. And finally, after solving it, I will be having the value of this constant k as equals to 2 upon r square. So further, my formula for the Gaussian distribution has been reduced to this particular equation. It says the number of particle concentration at any point xy in the cross section in a slice will be equals to n naught, the maximum number of particle concentration, into exponential minus 2r square by r square, that is capital R square. We know that what is capital R square? Capital R square is nothing but the radius which is defined as where the powder density is 1 by square of its maximum. Now let us try to find out the value of this n naught in terms of some known parameters. So what is known to us? We may know that there are total number of particles available in a particular slice, and I am writing it as np. So let us try to find out the value of n naught in terms of np. So how can we do that? Let us assume that at a distance r, I have a strip of width dr in this zone only. Now in this region which I am hatching here, only in this region or in this strip, the number of particles will be NaXY into the area of the strip, because this function is telling me the number of particle concentration at any point xy in this area. And if I consider this small strip as area, then the number of particles in this strip will be equals to nothing but NaXY into the area of the strip, that is 2 pi r dr. Now, if I want to calculate the number of particles in the whole zone, I mean in the entire zone, then I can integrate it from 0 to infinity. Why infinity? Because we have assumed that the distribution is Gaussian. So, at infinity also there may be some particles due to the nature of this asymptotic curve with the axis r. So, now the total number of particle Np in a particular slice will be equals to integration 0 to infinity NaXY into 2 pi r dr. Let me now replace this NaXY by the expression which we have derived earlier, and I will have this equation. Further, after solving it, this equation here, I can obtain N naught equals to 2Np divided by pi r square. Now, I can replace this value of N naught, which is the maximum powder particle concentration, equals to 2Np. Np is the total number of powder particles in a slice divided by pi r square. So, if I replace this value, finally my concentration of powder particle at any location xy in the slice A will be equals to 2Np by pi r square exponential minus 2 small r square divided by capital R square. So, now we have got some idea that if there is a stream of powder which is following the distribution of the powder particles by a Gaussian rule, then at any location at a slice we can find out the concentration of powder particle by a formula derived here. Now, let us use this analogy for our coaxial nozzle. So, this is our coaxial nozzle. We are not interested in zone 1 at all, because in zone 1 we are going to have a donut kind of distribution where there will be no powder particle at the center, but the powder particle will be in a zone which is annular here. However, we are interested in zone 2 and zone 3. So, now let me consider any cross section. Let us consider first the cross section A dash B dash. Here we can have a very large diameter of the powder stream, but will not have any empty space, and the powder particles will be distributed like this. Let us assume that this distribution of powder particle in zone 2 and zone 3 is followed by a Gaussian function. Then I can write my equation which I just derived, that if it is following a Gaussian equation, then the number of powder particle concentration at any location xy in a slice A will be equals to 2Np by pi rz square. Now, please note that earlier I have considered this radius of the stream constant, but here if you see zone 2 and zone 3, in the zone 2 the powder particles are converging, and in zone 3 the powder stream is diverging. Due to this convergence and divergence of the powder particle stream, I will not be having a constant value of the r. However, it will keep on changing, but it is not a very difficult task to obtain what will be the value of this rz. So, let us write it as a function of z into exponential minus 2r square divided by rz square, where z is the powder defocusing distance and rz is the powder flow radius reaching 1 by square of its peak powder concentration when powder defocusing distance is z, taking the powder focus as a point as origin. So, where is the origin? Let me just define that first, then we will move further. So, the origin is here and its value is positive towards the down. So, this is the z axis, please note that, because this convention of sign is important now. So, this is the origin, which is, let us call at 0, z equals to 0 here, and it's positive downward. Now, assuming the effect of the powder gravity is neglected, the powder flow radius Rz in any of these zones, zone 2 and zone 3, can be easily calculated. Let us first consider the zone 2. So, if my powder particle stream at the top is coming with an angle alpha from the horizontal, as you are seeing here. So, this angle is alpha. Also, it is known to me that the radius of the powder stream at the focal point is given by Rp, radius of the powder stream at the focal point. So, this distance is known to me, OB is known to me. Now, I can easily find out anywhere in zone 2 the radius. So, let me just make a small triangle over here, this triangle. The angle is given to you as alpha, this angle is alpha, therefore, the angle between this line and this will be alpha, this will be 90 minus alpha, and if this is 90, of course, this angle is going to be again alpha. So, if this angle is alpha, and let me write this point as, for time being, as P, then I can say tan alpha will be equals to PB divided by PB dash. And what is this? And what is the value of this PB? It is nothing but the distance Z measured from the origin. And if I am measuring in upward direction, it will be nothing but minus Z. So, anywhere it will be written as Z. So, let us write it as minus Z. What is this value of PB dash? That is of my interest, and I am going to calculate it as, and writing it as PB dash. So, finally, the value of PB dash will be equals to minus Z cot alpha. So, this is my distance PB dash, this distance from here to here. Therefore, now I can easily find out the radius of the powder stream at any location Z unit above the origin. I know this value is Rp, and addition to this, the radius of the stream at this particular height is Rp plus PB dash, and we have already seen the value of PB dash is coming to be minus Z cot alpha. Therefore, the radius of the powder stream at a particular height from the origin will be Rz equals to Rp minus Z cot alpha, and it is valid only in zone 2. Now, let us come to the zone 3. So, this is my zone 3, and assume that after getting converged, the powder particle stream is obtaining a minimum radius at a focal point, and after that it is getting diverged, and the angle of diversion is given by this angle alpha, this angle beta. Now, if I consider anywhere any cross section in this zone 3, I will be able to calculate the value of this R, as anywhere if I go down, the value of this R is getting increased. So, let us try to find out. In that case, also Rz will be equals to the Rp, that is this distance OA, this distance is Rp, already known to us, plus if I consider this particular triangle here, this particular triangle, I can find out the value of this particular length from here to here, and it will be nothing but Z tan beta. Therefore, I can say at any height Z, the value of the Rz, the radius of the powder stream, will be equals to Rp plus Z tan beta. Hence, in zone 3, we have got the radius also. Also, we can easily find out the value of Rp, the radius of the powder stream at the focal point, in terms of the fixed parameters. So, for that, let us just consider this diagram again. Here we are saying that the focal point is achieved at a height Fp from the exit of the nozzle, So, this is also called as focal distance. This is Fp. Also, the angle at which I am injecting the powder is given here by alpha. Also, the distance between this particular point from the center of the nozzle is given by r naught. So, if these three values are known to me, I can easily find out now the value of OB or OA at this particular location. So, let us see that. So, I am cleaning this area. This distance is known to me from here to here. It is FP. Now, I am interested in finding out this distance. As this angle is alpha, therefore, this angle will be also alpha. So, let me write it as alpha. So, this angle is alpha, therefore, this distance from here to here will be nothing but FP divided by 10 alpha, or in other words FP cot alpha. Now, the distance from here to here is already shown here by r naught. So, this distance is r naught, therefore, the radius of the powder stream at the focal point, which is shown by this distance, will be equals to rp equals to r naught minus fp cot alpha, that is this distance from here to here. So, as now I know the value of Rz anywhere in the zone 2 and zone 3, I can easily apply this formula to obtain the particle number concentration anywhere in these zones. So, now let us assume that the upper surface of the molten pool created by the laser beam. So, if this is the laser beam coming and it is creating a molten pool over here, it will look something like this in the side view. But if I look from the top, we are assuming that it is nothing but a circle, and this circle is represented by this radius, and the radius of this circle is nothing but W by 2. So, what is W here? W is nothing but the width of the bead you are going to obtain, because the powder particles, those will fall inside this molten pool. Molten pool, when I am saying, means the zone in which the temperature is above the melting point. In this zone only the powder particles will get melted and create the bead. Therefore, if I am assuming that the width of this zone is W, then the spot size should be assumed to be as having a radius of W by 2. So, I can say that the molten pool is shown by the boundary x square plus y square equals to W by 2 square, where W by 2 is nothing but the radius of the circle. Now, let us try to find out the efficiency, the catchment efficiency of the powder. The catchment efficiency or the primary efficiency of the powder can be expressed as the ratio of the quantity of deposited powder to that of the total powder fed into that zone. Since only the powder particles trapped in the pool are deposited, given that the pool surface is shaped as circle, the primary efficiency of the powder particle is represented here by eta p, can be easily expressed by this formula. So, what it says? So, it says the eta p equals to double integral sd and a xy ds. So, this is the area integral for the distribution of the powder. So, mathematically it is represented here. So, physically, if there are so many powder particles here, we are trying to find out the powder particles, those are coming under this zone only. So, as it is a 2D area which is represented by a circle, I have to obtain the area integral of this distribution in this zone. So, that is very easy. First of all, let me just consider that this area of the melt pool is represented like this. It is having a radius r. So, if I consider a small element at an angle theta of d theta and at a radius r of dr radius. So, if this is a small element I am considering, the area of this element will be given by this length of the arc, and length of the arc will be r d theta into the distance dr. this will be the area of this tiny strip. So if now I integrate this theta from 0 to 2 pi to complete the circle, and the radius from 0 to w by 2 from here to up to the periphery, that is nothing but the radius of the circle w by 2, I will be able to obtain this integral. So here if I replace this value of naxy from the previous expression, it will be 2np divided by pi rz square exponential minus 2r square divided by rz square into the area of this tiny small element, that is r dr d theta. Here the np is nothing but the number of particle, total number of particle in the cross section. So if I am considering a cross section here, I am trying to find out the total number of particle in this zone. So as np will get cancelled, this term will no longer remain in the efficiency. And this integration can be easily done, because now we know that if you first integrating this particular term, I can replace 2r by maybe t, and then definitely 2r dr will be equals to dt, and if I follow this, I can easily integrate this equation. Finally, you will get this expression after integrating it. It says the primary efficiency or the catchment efficiency NP is equals to 1 minus exponential W square, which is nothing but the width of the bead deposited, divided by 2 RZ square. So here we have already discussed, whenever I am saying width of the bead, it means the diameter of the melt pool. So it can be seen now from this expression that the catchment efficiency or the primary efficiency of powder is a function of melt pool radius and the powder flow radius. So it is a function of Rz also. So what is R? So it can be easily seen if I defocus, right? If I defocus my powder stream, of course this value of Rz will increase. As a result, this function will decrease, and if this function is decreasing, this entire function will increase, and as a result the efficiency will decrease. So with the increase of Rz square, definitely my catchment efficiency is going to be reduced. And also it can be noticed that it decrease or increase with the exponential function. So any change in the radius we are obtaining at the substrate will substantially change your catchment efficiency in the coaxial nozzles. So that is why it was very important for us to understand that how and why it is going to affect the final catchment efficiency of your process. Now once we know the efficiency or primary efficiency in which the powder particles are getting trapped into the molten pool W, then we can easily find out the mass flow rate in corresponding to the deposited bead. So the mass formation which is forming a bead at the substrate, this rate of formation of this mass can be assumed to be as mass in, meaning to say this much mass of powder is getting into the bead which is getting deposited. So this mass in will be equals to, if the mass flow rate of the powder at any cross section which will remain constant is given by Np, is multiplied by the efficiency of the powder particles, those are getting trapped into the molten pool, then we can easily find out the mass in, that is M in equals to Mp into eta P. So the mass of the powder which is going into for formation the bead will be equals to Mp, which is the mass flow rate of the powder, into 1 minus exponential minus W square by 2 Rz square. So now we know how much mass is going in to create the bead. However, it can be noticed that catchment efficiency is considered to be only based on the projection area. You have a small molten pool and the powder stream is larger than that. Therefore, the catchment efficiency is coming into picture. The area of the stream is larger and the area of the molten pool is less. But there are other issues also which further reduces this catchment efficiency. The primary region we have seen and we have called it as primary efficiency. That is why there are few more reasons, like the powder particles are usually coming with a very high velocity and they may not stick to the melt pool. Instead, they just strike and go here and there. And that bounce off of the particles here and there is what you see when you see any video that sparks generated, those particles. They are nothing but bouncing of particles after striking the melt pool. And that is usually not very high. That too is around 30 to 40% of whatever particle you are injecting. Even though they are projecting towards the molten pool, not all the particles are going to trap. Around 70% of the material of that also, that I am telling with a very crude idea, it may further improve also in some of the systems, but approximately 70% of that powder also get waste here and there. So that efficiency, if I assume to be called as utilization efficiency, and I multiplied this equation with that efficiency too. So now I can finally say that the mass in to form the bead can be given as M in equals to MP into NU and this expression. So this is mass in. Now let us try to look at the deposited bead side, that how much we are forming the bead if the shape of the bead is known to us. So let us assume that the bead cross section is following a parabola shape. This we have already considered in the case of worm also. That is why we are considering the same thing here as well. We are considering the shape of the bead as a parabola. So this axis I am considering to be as y dash, and this axis is z dash. So the width of the bead is w and the height of the bead is h. And if I am saying this curve which is shown here in black color is following a parabolic shape, then of course I can write as z dash equals to a y dash square plus b. And if I write these boundary conditions which says that at y dash equals to 0, meaning to say at this particular location, z dash will be equals to h. As a result, your b will be nothing but h. And if I put another boundary condition which says at z dash equals to 0, which is at this location, the y dash is equals to w by 2. In that case, your a will be equals to minus h divided by w square by 4. So by putting these value of the constants into this equation, I will get the equation of the parabola as you are seeing here. It says z dash equals to minus 4h by w square y dash square plus h. And of course, this equation is valid for z dash greater than 0. Of course, here w is the width of the track and h is the height of the track. Now I can easily find out the mass of this bead. The mass will be equals to nothing but the density into the volume flow rate, the rate by which it is getting deposited. So assume that you are moving your nozzle with a speed Vs, that is also called as scanning speed or travels speed, by which you are depositing the material on the substrate. If I know that, I can easily find out the V dash because I know the area, the cross section area of this bead, and in the transverse direction perpendicular to this area I am moving with the velocity Vs. Hence Vs into AB will be nothing but the volume flow rate onto the substrate. Therefore, the deposited mass will be equals to rho Vs AB. Now from here, so now here I need the value of AB. AB will be nothing but the equation of this parabola, and we know that it is equals to 2 by 3 WH. If any of you having any doubt related to this area, you can just integrate it, the area under this curve. It is very simple, you can just do the double integration here to find out the area under the curve. It will come as AB equals to 2 by 3 WH. So now I can see the deposited mass is coming to be MS equals to 2 by 3 Vs WH rho. So this deposited mass onto the substrate and the powder flow rate coming towards the substrate into the molten pool, considering the efficiency of bounce back also, should be equal. Once we make sure that these two mass flow rate are equal, and they have to be equal, I can easily have a relationship between the height and the width of the deposited bead. So considering the mass conservation, MS equals to M in, I will be having 2 by 3 V as WH rho equals to MP and U bracket 1 minus exponential minus W square by 2 RZ square. By further solving this equation, I can get this expression for the height of the bead. Now H is given by this expression. In our previous case, we have already seen if we consider a point heat source and do lot of approximations, the width of the molten pool can be obtained as W equals to the peak power divided by 2 pi K Tm minus T naught. This is the width of the molten pool. Also, it can further improve by considering instead of a point heat source, the surface heat source or even the volumetric heat source. So, this width of the melt pool can be easily obtained by considering the appropriate heat transfer into the substrate. Once I know this value of W by utilizing either the Rosenthal equation or any numerical simulation, I can find out now the value of H. Even sometimes we perform experiments also, like we deposit a track and we can easily measure the height of the bead anywhere by even utilizing the vernier caliper. Once you know the height of the track, you can find out the width of the track by using this formula. So, in the end finally, you are now having the value of width as well as the height you are going to obtain. With this value of height and width, you can find out the layer thickness, and that will be nothing but the multi-bead problem which we discussed for worm. That says if there are two beads and those are of parabolic shape deposited side by side, the optimal step over between the center of these two beads should be equals to 2 by 3 of the width of the bead. And we also have a relationship between the width and the height, and now we can easily find out the distance which should be between the two consecutive passes. Once we obtain that, the height of the layer is also known to us, and now we can process further. One very important thing about this formulation is also that, for example, you are realizing a overhang feature, right? And if to realize this overhang feature, first is of course you can tilt the part and build like we preferably do in the case of powder feed additive manufacturing. But we can also utilize the adaptive slicing. If you recall, we discussed in our module 2 that adaptive slicing says we change the layer thickness based on the constraints given on the minimum possible overhang feature. So, if I defocus my powder stream onto the substrate, meaning to say instead of having a very high concentration, I lift it up a little bit, then in the zone of the molten pool, less powder particles will go. As a result, your height of the bead will decrease. Therefore, in the process itself, you will be having very low catchment efficiency, but you can be able to obtain the variable layer thickness just by changing the distance between the nozzle and the substrate. So, appropriately just by changing this distance, you can obtain different height onto the deposited bead, and therefore you can take the advantage of adaptive slicing for realizing the overhanging feature. Now let us discuss about a few major defects into the powder feed AM process. So, the first one is the porosity and the lack of fusion and the keyhole. These all are usually measured by something called as the dilution ratio. So, this is a typical cross section of the deposited bead. Here this one is the deposited bead and this is the substrate, and what you are seeing here in black color on the substrate, that is possibly the HAZ, heat affected zone. Now our focus is on the deposited bead. The value which is getting penetrated into the substrate is represented here by delta, and the bead which is deposited over it, the height of that bead is represented by beta. Therefore, the dilution ratio is given here as alpha equals to delta by beta plus delta into 100. Of course, in the case of additive manufacturing, it is preferable to have a relatively high value of alpha as compared to the other application for the same. Like if alpha is greater than 30%, the optimal range of dilution ratio between the first layer and the substrate is around 10 to 30%. What happened when we go beyond 30%? The keyhole effects occur, meaning to say a high penetration into the substrate occur, and it keeps on giving you the keyhole effect, which is not really desirable in the additive manufacturing, because in that case you may even destroy the previous feature which you have deposited. For example, you have deposited an overhang, right, and the overhang feature is only of 2-3 mm. Now you are depositing onto this overhang zone, and you are depositing with a very large dilution. So what you will end up doing, you will just destroy this feature itself. It is also important that this dilution ratio should be greater than 10%, because if the dilution is less than 10%, in that case you will be facing the lack of fusion. The deposited wheel will not fuse appropriately with the substrate everywhere. It may be having some lack of fusion at some portions. And of course, both of these will lead to the porosity. Usually, to control this dilution ratio, a function called global energy density is used. It is given by the power of the laser used divided by the traverse speed into the diameter of the laser. So, for starting with any new material, this global energy density is used to investigate the interlayer and intralayer porosity due to lack of fusion and the keyhole. The region with low global energy density are subjected to lack of fusion, and the region with high global density are subjected to the keyhole deposition, and both of them induce the porosity. Therefore, this global energy density should be optimized in such a way that your dilution ratio is within the range of 10% to 30%. Other defects in powder feed additive manufacturing are quite similar as we discussed for TIG and MIG based worm. Those are the residual stresses, the porosities, and the crack and delaminations. Now let us discuss about some of the major applications of powder feed additive manufacturing. The first is the capability of realizing the functionally graded materials. So, functionally graded materials are the objects whose properties are designed to vary in different parts of the product such that the local properties of the material in a part are suitable for the design function of the part. Some of the natural functionally graded material like the human bone and this coconut fruit is shown here. So, in this example of human bone, you can see the density of the material is quite high at the periphery and it is quite low in the inside region. So, this high density at the periphery and low density when you go inward shows that how the material property can vary as per the distance, and this is a density based functionally graded material. Now, this one is an example of material based functionally graded material. Here the material itself is changing when you are changing from one location to another location. Here it is a hard material, then there is a fruit, and then inside there is a liquid also. So, keep on changing the position, the type of material itself is changing. There could be other functionally graded material, there the part will remain of same composition of same density, but the color may change. That may be called as the color based FGM. Also, the FGMs can be further classified based on the gradient, meaning to say there could be a stepwise gradient. Suddenly there is a change in material like you are seeing in this object. So, it is a stepwise gradient, but it could be also possible to have continuous gradient, means the change in the property is continuous. It is not following or having any stepwise curve. So, for example, as you see, if I say this is the part having high density in this zone, maybe up to this location only, and suddenly after that the density is changing, and then suddenly in this zone density is further changing. So, I can make a sharp line and say that in this zone to in this zone density is rho 1, in this zone to zone density is rho 2. So, this is stepwise gradient. But if I am not able to find any particular line and say that beyond that or after that the value of the material or the metallurgical property is different, then it is the continuous gradient. We can make the functionally graded materials by the powder feed based additive manufacturing also. So, by powder feed based additive manufacturing, the FGMs can be realized very easily. Like I already mentioned, FGMs are characterized by gradual transition in either composition or constituent or microstructure, example grain size, texture, porosity, etc. along at least one direction. And also this variation should definitely lead to a functional change associated with at least one property. So, obtaining FGM in the build direction is far more challenging than the FGM along the build direction. So, obtaining the FGMs in the build plane is far more challenging than realization of FGM along the build direction. So, build plane means, for example, you are depositing in this plane and the entire area is filled by multiple passes. For example, this is pass 1, this is pass 2, this is pass 3, like this. There are several passes to fill this area. So, varying the composition in this build plane, so in this build plane which is XY plane, is far more challenging than creating or varying the composition in the build direction. So, why so? Because when you are depositing material, for example, along this track, and if you want to change the composition, for example, we want to change the composition from material A of maybe 100% at this corner, at this side, and material B which is 100% at this side. In between, for example, A and B are varying linearly. So, here B is 0 and here A is 0. Now, if you are moving along this track, the requirement is the percentage of A and B should vary along with your XY coordinate while moving the deposition nozzle. So, in that case, for example, let me just write a particular NC line. You used to write the some coordinate corresponding to X, some coordinate corresponding to Y, then you write the type of interpolation required, and then additional command will be required. So, here additional command will be required to change the composition. So, there should be a online variation in the composition, and that too should happen immediately after giving this command. However, it is not really a very easy task, because it takes some time to vary or to obtain the desired composition when we give this command to the nozzle, because you have seen the powder handling system are consisted of several subsystems. So, if you are going to change the percentage of one material to another material, definitely there will be a delay in that, and that delay should be accommodated here. So, that is why I said it is difficult in powder feed based additive manufacturing to vary the composition in the XY plane. But please note that it is possible. It is difficult, but it is possible, because if somehow, let us take an example, we are creating a molten pool, and in that we have multiple nozzle, nozzle 1, nozzle 2 and nozzle 3. Now, if required, we have the control of the mass flow rate of nozzle 1, nozzle 2 and nozzle 3, and by appropriately changing the mass flow rate from M1, M2 and M3, I can control the composition I am creating here. However, please note that if I am going to deposit this rectangular bead, for example, in that case, and from this end material 1 is coming and from this end material 2 is coming, it is of course true that the bead created may be rich of material 2 on one side and it may be rich on material 1 on another side. Therefore, definitely a mixing mechanism may be required to obtain the FGMs in the XY plane. But however, if we consider the FGMs along the build direction, that is quite easy, because while depositing one layer, the composition is fixed. Maybe we can say that the composition in the entire layer is not varying from one composition to another composition, instead it is fixed in a particular plane. So, let us consider this particular example. Here if you see, the bottom layer is pure SS316, while the top layer is pure SS430, and this composition vary may follow a particular curve here. So, in order to obtain or in order to deposit the material at different layers, so for example, if I take any layer in between, the composition may be fixed. So, let us assume that in this particular layer SS316 is 70%, while SS430 is 30%. So, this variation is quite possible, because before starting the deposition of this particular layer, I can set my composition appropriately, and then I will start depositing the material. As there is no instantaneous change in the composition required, it is quite feasible and has been explored by many researchers. How it works? As you can see here also in this diagram, if you are having multiple nozzles, for example, these are the two nozzles corresponding to one material, here it is written copper, and other two nozzles are corresponding to another material which is written here as tool steel powder. Now, some particular flow rate of the mass of powder is coming from these nozzles, and that will remain constant for a particular layer. Then after that, after realizing one layer, then the composition will change, and then after realizing next layer, the composition will further change. So, when realizing the different layers along the build direction, therefore, the mass flow rate coming from M1 and M2 and the mass flow rate coming from M3 and M4 will change appropriately to obtain the desired composition in one layer. However, like I have already mentioned, if you are having two nozzles, one is depositing the copper, another is depositing tool steel, it may happen that one side of the deposited track, this is the top view of the same, one side of the deposited track may be rich with one material. Here you can see it is rich, the one side is rich with copper, while the another side is rich with the steel. So, there may be requirement of a proper mixing mechanism. The another far most advantage of the powder feed based additive manufacturing is its capability of realizing the large scale components and feature addition on the already built parts. The powder feed based additive manufacturing can be used for manufacturing of very large components. For example, the Lens 850R system by Optomec has a very large work envelope of around 900 by 1500 by 900 mm. The machine can be used to build or repair the very large volume components such as blisk, impeller and shafts. Not only that, these nozzles can be mounted on the robotic arms, and those robotics arms then correspondingly retrofitted on linear tracks. In such a way, you can really increase the work envelope to a very high extent here. Like I said, another very important application of powder feed based additive manufacturing is its capability of realizing features. So, the features can also be added on pre-built layer or pre-built parts using this powder feed based additive manufacturing. However, further challenges like cladding or feature on internal or difficult to access location can be addressed by appropriate design of the cladding heads. So, if you see this particular head, here one can notice that the nozzle is very long, and this particular head, the nozzle is very long and the diameter is quite less in this case. The slim nozzle is particularly used for easy accessibility and long reach of the deposition tip to add the material at very remotely available locations to build the part. This type of slim nozzles are very suitable for its capability of easy accessibility and long reach to deposit the feature. Also, if you look at this particular nozzle here, this particular nozzle is meant for realizing the internal features on a cylindrical surface. So, here one can see this is the cylinder on which this particular feature is getting built, and to build this internal feature, the nozzle is at a 90-degree tilt. The powder streamline is at 90-degree tilt. So, this is the streamline of the powder, then after reaching here it is tilting by 90 degree, and then it is reaching towards particular location. Of course, there must be a mirror also for deflecting the laser also and creating the molten pool here, and in that they are depositing the material to realize the internal features. So, as I said, to make these nozzles accessible to difficult to reach locations, the nozzles has to be modified as per the requirement. The another conventional as well as the application of the same powder feed based additive manufacturing system is for making laser cladding and surface alloying. So, the laser cladding or alloying is a process that attempts to modify the properties of the base material surface using a similar or dissimilar material by melting both in order to obtain a new surface with the desired properties of corrosion and wear resistance and hardness. As you can see here, the base material is steel and top of this cylindrical surface Inconel 625 cladding has been done. Now, this cladding layer will protect this base from the wear as well as it will increase the hardness of the same. This is another example for the drilling head for the oil field, where you can see the cladded layer on top of the base surface. And we can also have the multiple layers or the multiple zones corresponding to the cladding, as you see in this diagram also. Here the substrate is of a different material, then there is a cladding zone and there are some alloyed layers also on the top. The major applications for cladding and surface alloying are like in the shaft, rods and seals, wall parts, sliding walls and disc, the cylinders and rolls, the turbine components, sealing joints and joint surface, tool, blade and molds. The another very unique advantage of powder feed based additive manufacturing is its capability of part restoration. So, for repairing purpose, the damaged part is first digitized and to create a CAD model later on. This CAD model is now an input which can later be realized for extracting the repair volume and tool path planning for that particular portion. The ability to repair the components increase the service life, reduce the cost of operation and promotes design freedom. An example of the same is shown here. As you can see, at the first stage, there is a turbine blade which is completely manufactured by the powder feed based additive manufacturing. So, this is a complete blade. After using it, the turbine blade got damaged after some time when its life got over, and the damage is occurring only at this location. So, the idea is now we scan the whole thing and identify the region where the repair is required. Then, if this is the volume required, the repair, we just consider this particular volume, do its slicing and obtain the tool path. Then bring this part to the DED where there will be a deposition gun and it will start depositing the material only in this local area. After deposition, then you can see the part has been restored to its previous condition. Here in this particular case study, the number of layers are around 18 and the powder flow rate was 20 gram per minute. The scanning speed was 11 mm per second and the laser power used was 375 watt only. The recent emerging area of the powder feed based additive manufacturing is the grid stiffened structures. So, the grid stiffened structures are conventionally plates and cell members backed by repetitive patterns of ribs and layout in a specific geometric configuration. So, for example, this is the part you are having, it is almost a plate kind of a shape. Now, to make it more stiff, here as you see, some ribs are deposited and they are following a pattern to repeat themselves on the entire surface. This is called as grid stiffened structure. The grid stiffened structures are popular due to their high load carrying capacity with minimal structure weight, or in other words we can say high strength to weight ratio. As the strength to weight ratio is high, definitely the parts created in this method will be quite economical as well. So, particularly what these rib structures do they prevent the local deformation on the plate and absorb vibration and process high bending stiffness while providing convenient mounting points for other structure members and machine components. So, this is another case study by Beam France, in which they have deposited these grid stiffened structure on a free-form surface. And of course, it is quite efficient and easy if I deal with the powder feed based additive manufacturing to realize this grid stiffened structure on the non-planar surfaces. Here, a deposition gun can appropriately travel along, where a tilt table will make sure that the deposition nozzle is always along the normal to the surface at which it is depositing right now. So, till now we have discussed about the powder feed based additive manufacturing. Now, let us just summarize our discussion in terms of the advantages and disadvantages of the process. Of course, the first advantage of the powder feed based additive manufacturing is its capability of depositing the material with a very high deposition rate that may go up to 3 kg per hour. Also, its possibility of realizing the material based FGMs, where you have seen multiple nozzles can deposit different materials, and based on the appropriate composition and based on the appropriate mass flow rate, the desired composition can be obtained. Part restoration is one of the very unique capability of these powder feed based additive manufacturing system, where the damaged portion of the part can be recreated. The same system of powder feed based additive manufacturing can be used for cladding operation as well, where a layer of the different material is deposited on the surface of the part to protect it from the corrosive environment and improve its wear and hardness properties. Also, this powder feed based additive manufacturing allow the user to use any in situ process in between if required. Like if you are depositing the material, for example, on a substrate, after completion of the deposition of a layer, one can perform after deposition a face milling operation as well to remove some oxide layers from the top or to maintain the Z accuracy. Not only that, there are several other in situ operations possible with the powder feed based additive manufacturing process, because we can interrupt the process immediately after deposition of each layer. Here, another possibility is like we can use the similar laser. We can use a laser to perform the pinning operation on that, so that the tensile nature of the residual stresses from the component or the part deposited can be reversed in sign and converted to the compressive strength of the residual stress, which is desirable. However, there are few disadvantages also of the process. There is no explicit support generation mechanism here, and hence to realize any overhanging part, one has to tilt the nozzle or substrate appropriately and then build the part. Also, the layer height which we are able to realize by this powder feed based additive manufacturing process is quite high. It is around 150 micron, and as a result we know that if we are building a slant surface, we will end up having a very bad surface roughness, that is nothing but due to the staircase effect. Also, the tiny objects are not really possible by the technology. Other than that, low catchment efficiency, which I have already explained to you for the side feeding nozzle as well as for the coaxial nozzle, is not really very high. It comes because of two reasons. We have seen that one, due to the powder stream divergence, and another reason is high velocity of the powder itself. So with this, thank you very much.